This presentation will be on waves and vibrations. It should be going along with the notes that you have. You'll be filling in the blanks as we continue through the slides. We'll start out our discussion on waves and vibrations with a video. It is going to be showing a group of people performing a relatively familiar act to most people, but they'll be performing the wave. It was a group of people at Bristol Motor Speedway who decided that they were going to try and set the Guinness Book of World Records for the greatest number of people doing the wave. And the reason why I use this video is that each person is only standing up and sitting down. You stand up one time, you sit down. But when thousands and thousands of people all do it together, right, and they coordinate it, they are performing the wave. If one person stood up and sat down and you looked at just one person, it wouldn't look like much. But when you look at the wave from an outside perspective and you can look at it in the big picture, you see that each person standing up and sitting down ends up creating the wave when they pass on the energy from one person to another. Meaning that person can be thought of as a molecule. And in most waves, each molecule is not moving very far, just like the person isn't moving very far. But the energy is still being passed through the crowd. And you can see the energy by the people standing up. And it goes around and around, and people may have participated at this at different sports games or different events. It's not that uncommon, but the wave is a great way to picture how a wave actually works in the sense of science. Right? There's all different types of waves. We have people doing the wave. We have slinky waves. We have water waves that are crashing on the shore. Radio waves in the air. We have sound waves, the sound you're hearing right now, the light waves that you're seeing. All of these things reach us through waves. Right? Now, not all waves are the same, but they are all examples of waves. Okay, first of all, what is a wave? Right? A wave is a disturbance that travels through a medium from one location to another. Right? And you'll want to add this to your notes. Right? It's a disturbance that travels, right, through a medium from one location to another. Right? In the case of the stadium with the people doing the wave, the disturbance would be the energy causing them to stand up and then sit down. And that goes from one location to another. Right? A wave is the motion of a disturbance. Right? That's what it is. Okay, so it's the motion, it's the energy transferred through the medium. Medium could be material, right? The slinky could be a material. Water could be a medium. All of the air molecules in the air could be the medium. And that is what passes the energy from one place to another. Looking at our two wave types in this example. It's a very short video, and it shows a transverse wave and a longitudinal wave. Right. If you watch the video, you can see that the transverse wave, right, moves up and down, right, and you can see the wave moving through the coils from one end to the other. The longitudinal wave is actually being compressed, where if you pause it, you can look and see how some of the coils are pushed together very closely, and it travels through the wave. Whereas the transverse wave, you can actually see them moving up and down. So when a disturbance moves through a slinky after you push it, right, when you push one end, okay, it's considered a pulse. So the disturbance that is moving through this longitudinal wave would be considered a pulse. You can see the pulse moving through the wave right now, hits the end, and it stops. If I play it one more time, you can see that pulse moving through the wave halfway to the end. That would be your pulse. Right. And if you can, try to make a drawing of the longitudinal wave with coils. If you can, draw a compression as well. So you'll want to get that in the little drawing section of your notes. One more time, you can see the transverse wave move, where the molecules move up and down, or in this case, the coils. In the longitudinal wave, they're actually moving parallel to the energy. Okay, the coils are moving parallel to the energy, whereas the transverse wave, the coils are actually moving perpendicular to the energy. The energy in the transverse wave is still moving left to right. You can see it moving left to right in the transverse wave. But the actual wave itself only moves up and down. which is perpendicular to the energy. So we'll use a slinky as an example. Right? When a slinky is stretched out from end to end, it is held at rest. It assumes a natural position known as the equilibrium. So if it's just sitting there, it's at equilibrium. When water is sitting still, it's found as equilibrium. Okay, there is no disturbance. Right? We must create some sort of disturbance, meaning we have to get the particle to move away from its original position. Right? It has to move. If it's just sitting there, there's no energy moving through it, right? There is no wave. Right? One way to do this would be to take a slinky and to jerk it forward. So if you were to go back to that longitudinal or those compression waves with that slinky, you can jerk it forward, right? The metal slinky is the medium. Okay, so the medium in this case is the slinky. It transfers the energy pulse of the wave. So the metal of the slinky is the medium that transfers the energy pulse of the wave. You can see the disturbance would be being compressed together. It is a compressional wave. Right? It's being compressed. It's a longitudinal wave. And the energy is moving parallel to the slinky. Right? Again, the medium is the slinky, and it's transferring the energy. Right? And in this case, this example is a longitudinal wave. It's being compressed. Okay. What is being transferred? The energy is being transferred from one end to the other. Again, just to repeat, you can pause it if you'd like at any moment to read things if you'd like longer, but the slinky is the medium. Right? The medium ends up in the same place. It all goes back to where it originally was, or very close to it. But it moves to pass the energy along, and sometimes it can be going back to the original place. Just like in the stadium wave, the people stand up, they move, they end up sitting down back to their original place. A longitudinal wave, right? Or another name for it would be a transverse wave, right? Works a little bit different. Okay, so here we have the longitudinal. Actually, this is still the same example as before, right? So I apologize for that. I'm not moving on yet. I do want to show you the tuning fork. So when you see this tuning fork, you can see the fork is actually compressing together in slow motion. That's what's happening when you hit a tuning fork. And what it does is it compresses all of the air around it, and that's what creates the sound. Sound is compression waves or longitudinal waves that are reaching your ear. And you can see that tuning fork vibrate, and it ends up passing the energy from the tuning fork to your ear. And that's what you end up hearing. Okay, your next bullet point will be coming up with our transverse wave. But one more time, I want to show you a slinky now so you can see a longitudinal wave. Okay, a different video, but you can see the person is going to be compressing the slinky, and the energy is moving through the wave. It actually bounces back. Right there you can see it hitting that other hand and bouncing back. They're going to push it again, and watch when it hits the other hand and it bounces back. Hits the wall, okay, and it actually very, very slightly bounces back. And right about now, you can see the coils moving again because of the fact that it bounces back. So they push it, they're compressing it. That is a longitudinal wave. It hits the end, and a small amount of the energy does come back to the other end. Right? And that is a longitudinal wave. Okay, our second type is going to be our transverse wave. Right? And this is our fourth bullet point. Right? In a transverse wave, the pulse travels perpendicular to the disturbance. So that blue line right there, that's going to be what you're going to want to write in your notes. Right? In a transverse wave, the pulse travels perpendicular to the disturbance, meaning the pulse is traveling side to side, but the disturbance is actually moving up and down. On the left, you can see our compression wave. On the right, you can see our transverse wave, right, where it actually makes the loops, or not the loops, but the almost like a roller coaster, the hills. It looks like hills, and you can see that the source moves up and down, but the coils also moving up and down with the energy traveling side to side. Whereas a longitudinal wave on the left, you can see the coils are going to move left to right, and the energy is going to move left to right. Transverse, they're going to move up and down. The source moves up and down, so the coils move up and down, and the energy is transferred to the right. You can also wiggle a slinky back and forth. right? That would be the same. So using the same video series, you can see our transverse wave. This is the style of wave you'll want to draw for your drawing, right? Your 6th bullet point, I guess that would be. I guess the other one would be your 5th, considering your drawing bullet. But your second drawing will be the rolling hills, what it would kind of look like. But that is our transverse wave. You can see the coils just move up and down, and it's passing energy along. It almost looks like a snake slithering. You can see the energy bouncing back and forth. They stopped. You can still see it bouncing. So it continues to move, but that energy is being transferred side to side while the coil is moving up and down. Again, another visual for you to see the different types of compression waves where you can see them being pushed together. That's how you would actually draw a compression wave. That top drawing would actually be another one you'd probably want to add to your top drawing in your notes near where you drew your original coil being compressed together. But a lot of times this is what they'll draw it as. It almost looks like a UPC code. The anatomy of a wave. So if you look at the anatomy, we have different parts of a wave, right? A, B, C, D, E, F, G, H, I, J are all different points that we're going to be focusing on and pointing to, similar to the points that we use in the simulator that we had. So when we look at our anatomy, right, the dashed line represents our equilibrium. Equilibrium, right? That's the name for it. And the spelling is on the slide. You can pause it if you need to, but you want to write the word equilibrium with an arrow pointing to the dotted line. You can pause it and do that now. Okay, once the medium is disturbed, it moves away from this position, and that's what causes the wave. So if there was no energy moving in, that solid line would actually be straight, just like the dotted line. Here are some other points you're going to want to add to your anatomy of a wave. We have crest, basically the top of a hill. The crest would be points A and F. You'd want to label points A and F with the word crest. You can pause it now if you need to add those. Right, at this point, this is where it is as far away above, okay, or upwards, positive amount above the equilibrium. So it's upward movement away from it. Whereas the troughs are actually the bottom of that. Okay, the troughs are going to be at the bottom, right? That would be points D and I. Okay, it would be negative. It's because it's below the equilibrium. The greatest amount of movement below the equilibrium is what we call the troughs. Label that D and I. And we have our next bullet point that we're going to be filling in. Okay, the amplitude. Okay, the amplitude is the distance a wave moves away from the equilibrium. So if you look at the slide, the second bullet point on the slide will be the next one you'll fill in your notes. The amplitude is the distance a wave moves away from its equilibrium, right? And it wouldn't hurt to add amplitude to your notes as well with the wave drawing. With an arrow in between A and the dotted line, that's the amplitude. Amplitude does not go from A to D. Amplitude only goes from A to the dotted line. Your wavelength, which we have discussed this before, but wavelength is any point from crest to crest or trough to trough, right? Your wavelength will be from crest to crest or trough to trough. I would label that on your drawing, maybe with a line going from A to F. That would be a wavelength. Okay, that would be a wavelength. What else can we determine? Well, we can look at some other things. Right? We can also figure out what the frequency is. The frequency is the number of times a pulse passes a fixed point over a given amount of time. So how many times will a pulse pass by a certain point in a given amount of time? So if this wave, right, if 8 crests move by every second, the frequency would be 8 because 8 of them went by a certain point in a given amount of time. Right? And just to review, here's another drawing with our wavelength, our trough, our amplitude. You can see the wavelength is going from the middle point to the middle point of this wave. It doesn't have to be from crest to crest. It could also be from trough to trough. Amplitude is how high the wave is from the equilibrium. And the wavelength is how long it is from one point to the exact same point on another spot. Okay. Thank you for listening. That is part 1.